Welcome everybody to my talk. I would like to talk today about a tool that we've built at ThinkSelf called Typescripten. And well, the slide says what it's supposed to do. It's supposed to make web development in C++ easier, more convenient, and type safe. And before I go into the why do web development with C++ and then how to do it, I would like to start with a short code example that should hopefully make this pretty clear. So how do we do web development now? Well, there are two ways to do it, of course. There's the classic JavaScript way. So this is in the commented lines. You see JavaScript, which doesn't do much. It just creates an element on the side and displays hello CppNow. And in the colored lines, you see how you would do it now. This is using emscripten. So this is C++. It would compile. You see here we are accessing the global document object, which exists in the JavaScript world. And then we call a method on it, which is called createElement. And you already see the problem here. We call a function. We pass the function name as a string to the JavaScript side, so there's no guarantee that this actually exists. We have to try it out at runtime. If we have a typo, we won't notice. And we have to specify the return type of that function here explicitly. So this is not very elegant and error-prone. Wouldn't it be better if we could write something like this? So we call a method, we get the global document object, and then we actually call the createElement method that we want to call. So we create this paragraph thing. Same here. Let's set the text on this to hello CppNow. Okay, I'll leave the typo. Then we want to set the font size so you can actually read this in the back. Set this to 20. And then last but not least, we set this. We add this element to the body of our website. Okay. So my hands are still cold from the temperature outside. Okay, I'll save this. This is important in a coding sample. Okay. Now I'll just call the emscripten compiler. So this is the normal emscripten command line with some include specified. And now I'm adding two additional parameters, which are pretty experimental. They're so experimental, they only exist on my computer. But they should make it into emscripten if everything goes right. And those two parameters tell the compiler two things. Take the JavaScript DOM API and generate a C++ header for that I can include here and compile against. Okay, so I'm compiling. It's telling me this is all very experimental. Outputting some warnings we'll ignore for now. And then, of course, it takes a moment because everything that's getting better in C++ increases compile times. And then, it gives me an error message. How unexpected. Something is a bit slow here. Okay, it tells me, there's no matching member function for this call to font size. Why? I'm setting the font size. It says, candidate function not viable. There's no known conversion from int to string for the cascading style sheet font size property. And now remember what I know about web programming. The font size has to be a string because you have to specify a unit. Okay, how good that we have this checking compiler. We would never have found this problem otherwise at build time. Okay, now we try this again. Again, takes a moment. Luckily, it's the fastest laptop I could get. Because now it's, of course, parsing all this DOM library and outputting it into a header. That should work now. Okay, cool. So what do we see now? There we are, including the typo. So it's not staged. And not only that, but we can go in here. We see our C++ code that we just compiled to web application. We see that in Chrome in the debugger. We can reload, set breakpoints, and even debug this stuff, which is pretty cool. It's not much interesting to see here, but it's interesting to know that this works. Okay. So what did just happen? Well, you saw our TypeScript compiler in action, and this tool takes type information. It takes type information for JavaScript libraries that we get from TypeScript, and then transforms them into a C++ header. So we now have a type-safe C++ header interface for a JavaScript library. Why? Why do we do web development with C++ at all in the first place? Let me show you a quick example. Normally, we are a C++ company. We have a product, we develop it in C++, a million lines of code. And now recently, we try to do a very small web application. There's this Tableau.com online data tool, and we wanted to get data out of that and link it to a thing cell chart in PowerPoint. And in order to do that, we had to embed that in a website. So you see that here. So there's a browser extension, the user can click on a chart, and now you see the entire web application. So here's the data, and the user can specify mapping to the categories and series and values of a stack chart. And now this is going to be inserted in PowerPoint. So this was the entire web application. It has maybe 1,000 lines of code. And there's the chart. And it only has to do one interesting thing. This data here comes like in a long list of individual data points, and we have to transform this into the canonical tabular data format. So each data value can be a number, a string, or a date, and we had to sort these values, make them unique, and then do a binary search so we can put these values into a table. Pretty simple. Now I try to program this using TypeScript or JavaScript. So first, I wanted to sort this array of values. I looked at the documentation. It says, by default, JavaScript array sort will sort all the elements by converting them into strings and then comparing their code unit values. What? Exactly. This is not quite what I wanted. To be fair, you can override this. You can provide your own comparator. You cannot fix the second sentence. The time and space complexity of the sort cannot be guaranteed. Wow, that's... And well, then, not surprised, there's no make unique range algorithm either, and there's not even a binary search in the JavaScript standard library. So I'll try to be a good JavaScript developer, and I did what everybody does. I went to the NPM repository. I looked for binary search. And the NPM would helpfully recommend two things with very high quality. That's this lilac bar. The first one isn't actually binary search, of course. It's, well, a tree implementation. The second package is a binary search. So I looked into it, and it turns out it's not correct. At the very least, I remember it would overflow on large integer counts. OK. I would really like to program this like this. So the data value would just be a variant of those three things I can have, and then I can fill a vector of those data values by getting the results of my query. And then, for example, with the standard range library, you can sort them, unique them, and then last but not least, do a binary search with logarithmic complexity. So here, I would like to program this web application in C++ because, for a lot of reasons. Well, first of all, I'm familiar with C++. There was also always some code we wanted to share. Even in a tiny application, there was some data structure you needed on both ends in our native application and in the JavaScript application. I would like to reuse that. And last but not least, we have a pretty good standard library in a lot of cases. No matter how much we like to extend it, what we have is often very, very good. OK, so what do we need to get a little C++ application into a web browser? Well, we need three things. We need to compile C++ so it can run in a web browser somehow. Then we want to call JavaScript from C++. And last but not least, we want to make these calls type-safe. So how to get C++ into the web browser? That's where WebAssembly comes in. So that's not a very new technology. So this is only the talks at CppCon I could find. So this is going to be a very short introduction to WebAssembly for completeness sake. So WebAssembly, of course, is a compiled and binary format, which has been standardized and is supported by all major browser vendors, which is pretty huge for web technology. It's a very fast and compact format, and it has two low-level data types, integer and floating point numbers. This will be important. And every WebAssembly application runs in its own application sandbox, and by default doesn't have any interaction with the outside world. Now, WebAssembly modules are typically instantiated from and can interact with JavaScript. So here we have the JavaScript world in our browser, and here we have a WebAssembly binary in our browser. And now the WebAssembly binary has a function A, JavaScript has a function B, and WebAssembly can declare, well, I would like to import a function B, and I would like to export my function, and then the two can call each other. WebAssembly can also export its memory object, which is essentially an array buffer of integers, so JavaScript can access that too. This is how it would look in JavaScript. We implement two functions, which handle the error cases for our little application, make an import table, instantiate a WebAssembly module with the binary code we have downloaded from somewhere and our imports. And when that is done, we can call the exported functions on the WebAssembly module. So that's pretty simple. WebAssembly also has this nice text format, a bit like disassembly. So this is the WebAssembly text representation for the C string compare function. So you see it takes two integer parameters, which will of course be the pointers to the zero terminated C strings. And it returns an integer as well. Okay, and then, yes?
Were those I32 pointers?
Sorry?
Were those I32 pointers?
Those were I32 integers, yes. Yes, and they are limited to a 30-bit. I think the integer WebAssembly type is currently still limited to 32 bits. Yes.
So that's a pointer that you're passing.
Your interpretation is a pointer. In WebAssembly, there are only integers. But you see here, there's a special instruction. I think that's what it is, which would access this this blob of memory, this array of integers, essentially this array of bytes, and read data out of this memory blob at this integer address. So yes, for in C++, that's a pointer.
So this is like an M32 build?
Yes. That's only that's the only thing it supports. Yeah. Yeah. And now we need to wrap this all up together with some runtime support, and this is what emscripten provides. So it bundles both the compiler, which is Clang, of course, which has a WebAssembly backend, and then emscripten provides OpenGL headers, simple direct media layer API headers, interfaces to access HTML5 input events, and then implements them all in a JavaScript runtime library. And this is great. For example, it has been super successful for porting games to the web. So you have a very self-contained C++ application, graphics output, audio, and input device access is pretty much all it needs. And then this was great, was a great environment for porting such things. Okay. How can we call JavaScript from C++ in emscripten? Well, we've already kind of mentioned one way. The first way is that WebAssembly can import and export functions, so it can call JavaScript and vice versa. So in C++, you would just declare an extern C function, which you would then implement in JavaScript, and the WebAssembly machinery would link those two together. But these functions are then limited to data types that WebAssembly supports. So the return values and the arguments can only be integers or floating point numbers, which is, well, pretty big limitation. The second way is this direct embedding here, where emscripten provides a set of macros. And inside this macro, you can actually write JavaScript code, which then gets, I think it gets put into an actual section in the binary, and then it's somehow magically extracted and sent to JavaScript. In this macro, you can also pass arguments and return values, but these are also limited to doubles and integers. Yes?
So you can't do strings?
Sorry?
You cannot do strings?
No, and even if you would, what kind of string? Would it be a JavaScript string or? No, you can only do those two things, and we'll see how that can work with more complex data types. And then there's this API that I've shortly shown in the beginning, emscripten val, which is kind of a way to make a transliteration of JavaScript to C++. So this is almost a one-to-one translation from the JavaScript to C++. And I've already mentioned the problem in the beginning. So here, none of this is in any way type checked. It's all strings that will be sent to JavaScript and interpreted on the JavaScript side. And if you have a bug somewhere, it will find out at runtime. So starting with the pros, it's great that this exists and that it works, but it combines the disadvantages of both languages. So you need to compile it, which takes time, and then this compilation doesn't really give you anything. Okay, so how can we, how does it work? Yeah, how do we pass strings then? How can we pass strings? So this is based on a couple of runtime functions that emscripten implements in JavaScript that can, for example, create a new object, or create a new JavaScript string from a C string, etc. And what these do is they're implemented in the JavaScript side, of course. And then this function mValNewObject would create a new JavaScript object, an empty one, so it's opening, closing, brace, you're done, and would create a reference count, set it to 1, and then store both of these things in a map, the object together with its reference count. And then it will return an integer to the C++ world, so a handle to that JavaScript object and its reference count, which just live in the JavaScript world. We can also create JavaScript strings from C strings, which is a bit more complicated. That's what this function does. So you see it would receive a pointer to the C string, and then it would read that zero-terminated C string from this array buffer, from this memory object, essentially character by character, and append it to a JavaScript string object, and then store this in some JavaScript map as well, and return a handle to C++. So now you can have a handle in C++ to any JavaScript object, but it will always be just an integer handle. And now, of course, you can imagine the rest. We can implement functions that increase the reference count, decrease the reference count, remove the object from the map when the reference count falls to 0, and then call methods on that object. So what we want is to turn this, into something that looks more like C++, and that is checked at compile time. With the exception, of course, of this triangle parameter. So, and how do we do this? So this is the Typescripten project. You can find it on GitHub. Check it out there. There's also an example project with some CMake integration, so you can maybe play around with it. It's currently in progress to get this integrated into emscripten, as I've shown like in the first example. I mentioned this project on the emscripten mailing list, and Alonso Kai kind of liked it, so let's see and hope that that happens. And now I mentioned in the beginning, so now we come to the how does that all work, that we get type information from TypeScript. And this is how that looks like. So in TypeScript, you can write an interface definition for an existing JavaScript library. So a type annotation of an existing library, so to speak. And this is an excerpt of the document interface, of the standard JavaScript document object. You see here it has some base classes for sharing code. The document has a URL property, which is a string. It is read-only. It has an active element that can be null. Anchors are a collection of HTML anchor elements that looks very familiar to C++ programmers. The title is settable. It's a string, can be set and read it. And then there are interesting language structures, interesting descriptions that we'll come to. So this is how it looks like. And the nice thing is that these type definition libraries not only exist for the JavaScript standard library, that would already be quite nice, but there's an online repository of by now over 7,000 of such interface descriptions for really any JavaScript library you can imagine. A couple of popular ones, but probably a couple of unpopular ones as well. So it would be good if we could use all of those and have, well, a type-safe interface to those from C++. And the very convenient thing for us was the TypeScript already ships with a very powerful parser that we could just use. So we don't actually have to parse those files. We just have to do the other end. We just have to create the C++ header files for them. So this is the entire TypeScript code you need to read such an interface definition. You get the file, you create a program that instantiates the parser, evaluates everything. You get a handle to the source file you wanted to read, actually. And then you can iterate over all the top-level syntax nodes, for example, and check, is that node a function declaration? Is that a variable statement? Is it a class declaration? Then you can dig deeper. If it's a function declaration, what's its name, its return type, its arguments, etc. So that's the information we can use to create C++ headers. The result would look something like this. This is much simplified, but in spirit, it's this. So at the base, we use this emscripten API because it's very convenient. And we generate a type-safe wrapper for it with the type information we have. So we know there's a title property, it must be a string, and it returns a string. And then we just do the non-type checked calls to emscripten. Now, we do a translation between two languages, between TypeScript and C++, which are pretty different languages. And then we have to, like, from the get-go, we have to ask ourselves, oh God, do we have to, like, support everything that TypeScript can do? And this, for example, is valid TypeScript. So here you have a function. That function has an argument A, and the only requirement on the type of argument A is that it has a length property. So this would be pretty difficult, if not impossible maybe in that single case, but in general pretty difficult to express in C++. But luckily, we don't actually have to support all of TypeScript. We just have to support that subset, which is the one that is most frequently used in those interface definition files. In the worst case, we could change those interface definition files to make them easier to understand as well. What we see in practice, for example, is that programmers are very lazy, and they would maybe just introduce a type for that requirement, a type that has a length property, so we don't have to repeat that every time. And this now is something that looks pretty easy to translate to C++. That said, we support quite a lot of TypeScript's constructs. So there are a lot of built-in types that we support, of course, any undefined null, string. TypeScript classes can have optional members. There's a thing called type guards, which are a mixture of a type check. So you check if some object fulfills type requirements, and then you cast it to that type. There are union types in TypeScript. There are mixed enumerations. We can pass C++ functions or lambdas to JavaScript to be called as a callback. And there are also generic types in TypeScript, like arrays, records, etc. We support those too. Now, for a while now, the tool has been self-hosting. That means it understands enough of that to parse the interface definition of the TypeScript compiler API itself that we can then compile against. So that was, of course, a big step a while ago. And it can compile all the standard JavaScript libraries as well. This doesn't mean that it would correctly transform every single type in those libraries. Sometimes we just say, okay, this is complicated to translate. We ignore it, but it generates valid C++. Okay, and I said we use this API ourselves. Yes?
What exactly does that mean, that it generates valid C++, but you can't translate it?
Well, I can't occasionally, even in those standard libraries, there would be very complicated constructs, because TypeScript in itself is a pretty complicated language because it was meant to provide a way to describe in a type-safe way the entire complexity of JavaScript, which is in itself such a flexible language, but which made this quite difficult. So they have some language structures that would just be hard to translate, or that I haven't come to, intersection types or stuff. And then I come to that a bit. It's always okay to say, I ignore this single type and replace it with any, because I don't know what it is. But the output should be valid and is even usable because any is castable to anything. So you can call something.
Use the type checking for that thing.
Yes, that's the goal, exactly. So like I said, we use the same API itself, but now from C++. So it would look a bit like this. So pretty similar. And here you can see, well, we pass a C++ lambda to this JavaScript function that then gets called back for every syntax node. OK, so here are some of the many semantical differences between those two languages that make this an interesting project. So in C++, we have the one definition rule. In TypeScript, you can have multiple definitions of an interface with the same name, for example. And these could have different properties, and they would just be all lumped together into a single type with all of those properties. That's something that the parser does for us, luckily. The type system of those languages is very different. We have structural typing in JavaScript, or static typing in C++. The overloading rules are different, as I've just discovered recently. So here, for example, you have the declaration of the array type in TypeScript. And it has two constructors. One takes the length as a number, and then, well, it generates an array of that length with uninitialized values. And it has this variadic constructor. And now what happens if you call this? I would expect this to be ambiguous, but of course it isn't ambiguous. And maybe that's what you would hope. No, it calls the first one.
I would hope it calls the first one, because if it calls the second one, then there's no way to get the first one.
Well, then
I was thinking in Swift where you would have to say length colon before the 5. You say there would be a way.
Yeah.
If your argument levels were significant.
I tried it out. It calls the first one, indeed. And then, of course, there's quite a lot of built-in types in TypeScript that we have to now re-implement in C++. And then this is what I've just said about the priorities. Well, the priority is to generate valid C++ in the first place. And then in the second place, be somehow feature complete. So it's OK to ignore stuff as long as the output is valid. It's better than try to do it the other way around. OK, maybe something you've seen in the first code example, reasoning for the design decision, how we translate this JavaScript TypeScript statement to C++. So we could probably generate C++ that would look like this and do all the magic in the background. But that wouldn't be a very good decision, I would think. So at the very least, we have to do this. So we don't put everything in the global namespace. But this also has a problem, I think, that this looks like it's a very cheap access into some struct, when that's really not what's happening, and the operation is actually relatively expensive because it does so many calls to the JavaScript side. And I would like to expose that so people don't have unrealistic expectations. So at the very least, maybe it should look like this. Now it's a method, at least not access to a struct member. And I generated a title, a setter for the title. There's one other expensive operation that I'm hiding here, and this string conversion. So we also make this explicit. And yeah, this would be better. It's not pretty, but better, I think. And now I have one other problem. I have introduced a method name here that didn't exist in JavaScript. So we just had a title property in JavaScript. There was no setTitle function. I've created that. And well, it could be that the original object already has a setTitle function that does something maybe a little bit different. And that could create problems. So that's why we keep the name of the setter identical to the property name, which looks a bit unusual, but well, it takes an argument and it sets the property to that argument. But it would avoid naming collisions. Yes?
How to append to the title property?
Append?
Plus equal.
Aren't the strings immutable? Can you do that actually in JavaScript?
Yes.
Yes? I don't expose the. I think I've implemented the string type myself, and it doesn't have the operator. It should get the operators probably.
It's complicated, right? Because if strings are immutable in JavaScript, then what it's doing is rebinding the variable.
Yeah.
Right? And
yeah.
There's a whole complicated semantic dance there. Obviously, what you really need is projections so that you can.
No, luckily I was in your talk. I haven't implemented any overload operators actually for now. Okay, so this is why it looks the way it is, because now at least I avoid unintentional collisions between names. Okay, so what are some of the interesting aspects here in that translation? Well, there are a couple of simple ones. For example, in TypeScript, the declaration order does not matter. So this is valid TypeScript. We declare a union of two types before those two types are actually declared. We can't do that in C++. We have to collect all the types and reorder them in some useful order, base classes before derived classes, generate forward definitions, etc. to make that work.
So you wrote a whole program to do that?
Sorry?
You wrote a whole program to do that?
Well, I sort them. I mean, I collect them.
Yeah, but the TypeScript compiler is doing that for you, right?
Well, I'm not sure.
Maybe we could have that in C++.
Huh?
Maybe we could have that in C++. I mean, since you wrote a program that...
Yeah, you mean that so that this would become valid C++? Yeah, maybe. But I'm not sure it exposes its other ordering to me. I don't think it does that. You know, I can just go over the file. I cannot ask him for better ordering. I don't think it exposes that to me.
What doesn't expose that?
The TypeScript compiler API doesn't expose the canonical ordering to me, I think.
Oh, yeah, I didn't mean that. You can do the sort.
Yes.
You can do a topological sort.
I do, yeah, exactly, that's what I do.
And that's
yeah.
what the TypeScript compiler is doing.
Probably does
and
too.
maybe we could build that same thing into the C++ compiler so that we could have nice things.
Interesting
See what I'm
point.
saying?
Yes.
All right. Sorry.
Then there are union types in Typescripten. Union types are something very different from C++ unions. Well, first of all, they don't have a discriminating enumeration value. So this A or B or C type, you cannot ask, oh, well, are you A or B or C? Instead, it's more a set theoretic thing. This type is the intersection of properties of A, B, and C. So this type has exactly this set of properties. And well, because it's JavaScript and not C++, an object of this type, A, B, or C, is constructible from any other object of a type that has the correct property. So this is really what the TypeScript JavaScript type system looks like. So this is structural typing. A type is just defined by the set of properties it has and not by its name or its class relationships or anything. So of course, this is something that I cannot translate to C++ completely or at all, really. I can only find you don't.
Well, I mean, into existing C++, no.
Yeah.
Okay, no.
Yes, the one I live with.
Discussion in David Sankel's talk about whether we should have this in C++, and I think we could. We could, but for now I have to live with the C++ I have. Yeah.
But there are a couple of useful things that we can do that are valid C++ or expressible in C++ and valid in their original semantics. So I can say that this union type converts to common base classes of A, B, and C. I can say that this union type will convert to a wider union of A, B, C, and D, because that set can only get smaller. So that's going to be an OK conversion. And I can, of course, say that this type is constructible from anything that A, B, or C would be constructible from, because that has to have this property. And again, in practice, this is not actually as limiting as it sounds, because those programmers that write those TypeScript interface definition files are sane programmers, and they don't repeat themselves, but they just write this. And then this is something that I can easily translate to C++, and the resulting semantics are just what the programmer intended, even though they don't strictly match. So then there's here another customization point that might also exist when you do other language-to-language translations, which was interesting here for these mixed enumerations that TypeScript has. We can also customize the point where we communicate between like one of the runtimes and the other runtime, and send other data. So here in C++, we just generate a normal C++ enumeration and use that. And then we can do some template magic and do some template specialization of a type that tells us, well, how do you want to send this enumeration to JavaScript? And this contains a method, which contains a map. And that map tells us, well, the foo should be translated into a string and then sent to JavaScript. And the bar should be sent to a double. So we can customize that point for other data types as well. OK, so now I've said, which is maybe even interesting, that we can also send C++ function objects to JavaScript. So again, let me show you a small example. So here I have this website, which looks very unclean. I would like to clean this up, but this button doesn't work yet. I have to do this in C++. And here I have this prepared already. I don't have to code this. So we would just want to set this on click handler on the button that I have. But we cannot pass C++ function pointer to JavaScript. That's not going to work. We have to generate a JavaScript function object somehow. And the way we do that is with some macro magic, unfortunately. So here's the implementation of that. Something is funny with my code editor. Oh, OK. Of course, that happens in the talk and not before. OK, so here I have that implementation. Let's take that out, put it here. So, OK, now I have to do some macro, which just says, OK, I have this onClick function here. Please generate some helper code for me so that I can pass this to JavaScript. OK, what does this do? Well, it gets all the diff elements from the side. You see here as some generic JavaScript collection. Does for each of them, because we have written a range adapter for them that's using our thingsAllRange library. So, well, we have written an adapter for that. Each element, for some reason, is a union of that element and null. So we only take those that are not null. And then we sort those elements. That's what we wanted to do. We sort the element of the vector of HTML elements by the less with the less comparator, and we compare them by their client height. And then last but not least, we add them to the site again. OK, so now here I have created an object. That object contains this onClick callback. And now that should compile it the first time. Have I saved it? Yes, I have saved it. OK. So there you go. Works. How does that work? Well, in JavaScript, everything is reference counted, of course, including function callbacks, which makes thinking about things very complicated sometimes. So maybe sometimes you would like to program a simple state machine in your UI. You would say, well, I want to sometimes show this button. And when I create this button, then it creates its HTML thingy, and it registers its onClick callback. And then this is called sometimes. And then I want to take it down again. I want to remove that button, so the callback should never be called anymore. And this is hard to do in a reference-counted language. There's no deterministic destruction. This button could be held alive by somebody. It could be held alive by the callback itself, which captures this, which holds alive, keeps alive the button. It's complicated to do this correctly. And I always wonder when you have websites that suddenly don't react anymore in the browser, you probably know that, how often this is the reason that somebody messed up his state machine. Yes?
I'm slightly confused. This is JavaScript, right?
This is JavaScript now,
What
sorry.
is the underscore S?
It's a typo that I thought I corrected before. It's a typo in the slide. So this is TypeScript, to be more precise, because it has a real constructor. So we would like to do something like this in C++. Well, we have a constructor that does its thing, and then we have a destructor that cleans everything up, and it makes sure that this callback is destroyed and it's never going to be called again. And we can think about this, we can reason about this. Okay, so what do we have to do to make that work? Well, we generate a JavaScript function object with the right signature. And that JavaScript function object wrapper receives two arguments. It receives the function pointer to a static function we also have to generate. And it receives this pointer. And now internally, this JST function object will call into JavaScript. And in JavaScript, we have to create like a normal JavaScript function object, of course. That's what we need in the end. So this is creating a function object. When that function object is called in its call operator, it calls back into C++ and passes this captured function pointer back to C++. And now this function object here has one other interesting property or member. It has a detach function. So this thing has a destructor which will be called when we expect it to be called. And when this function object goes out of scope, it detaches from its reference counted JavaScript thing that can live for as long as it wants to, but it's not going to call back into C++ into a destroyed object, potentially. Okay, now this JavaScript function object is then returned, of course, captured as an emscripten value as a handle to that object. So this is the entry point in C++ again. We get our function pointer back. We get our this pointer back. We get the JavaScript call arguments back. And this function now has one task. It has to cast the function pointer to the correct signature, call it, and then we're back here in that generated function. That has one other task, unwrap this list of arguments because it knows the signature of our onClick function. And then finally, we are back in the code we actually wrote ourselves and can do our things. So this is hidden in that macro I've used to generate this function object that is interoperable between C++ and JavaScript. And now you've also seen in the examples that TypeScript supports generic classes, and we translate them to C++ templates, of course, because that's pretty much the same thing. And those TypeScript generics support a lot of constraints. So for example, in TypeScript, you can say that this generic argument should extend this enumeration, which means T must be one of the enumeration options. So when we support that, we can translate that into a template with a non-type template parameter. There's a huge amount of constraints that TypeScript supports that we don't support yet. So a very obvious one is that you can say that T should extend node, which to C++ programmers, again, reads like it should be a derived class of node. That's not what it means, of course. It means it should have the same properties. But we could translate it into something like that again. Like T should be a derived class of node. Again, that should probably work well in practice. But we don't do that yet. And now you've seen this other interesting signature here. And if you've ever programmed JavaScript, you know that this is kind of weird, that this add event listener function as first argument always takes a string that says which element do you want to, which event do you want to listen to, and then you pass a callback. And the event type of that callback depends on the string you first pass as first argument. Yes?
This event name and the event type, do they have a one-to-one relation?
We'll come to that. So this is the JavaScript way of this looks. And now the poor TypeScript programmers had to think of a way to express this relationship type safely in some sane way. So what are the sets of strings we can pass here, and how do those strings relate to the callback event types that we get back there? This is what index access types do in TypeScript. So this is what it looks like. So the TypeScript programmers thought, well, we'll introduce a type. And this type is actually just a map. It's a map of property names of strings to types. And then we'll say, well, our add event listener function as first argument takes some k that should be one of the keys of this document event map. So click or key down in my example. And then here in the listener function, they say, well, the event type is the result of looking up k in that map. That's pretty clever when I saw that for the first time. But now I have to translate that into usable C++. And well, there are a couple of ways you can do this, probably, many ways, probably. Yeah, sorry, that's the same explanation. So well, first you might think, well, maybe I can declare an enumeration of those two event types. Well, when I pass them as at runtime, that's probably not going to work because now I have a runtime parameter and I have to somehow figure out what type my listener should take. That is probably not going to work. I could take this enumeration value as a template argument. That certainly works. I'm sure you can make that work. But it looks very, very ugly. It also looks very, very different from the original JavaScript because this type doesn't really exist in the JavaScript world. It's just an invention in this interface library. So instead, there was a much more elegant way to do this with C++20 const expr string literals and some help by Boost HANA, actually. So this is how it looks like in C++, and this is how it compiles. And now how did that work? This document event map gets translated to this. So I have a document event map, and that has a const expr function that returns all the keys, which is a Boost HANA map. So it's a const expr map, which says, well, I have a click string and I have a key down string. These are valid property names. These are valid event names. And these are associated with the correct event for my event callback. OK. So probably anybody who doesn't know why I need this ugly template argument? For the compile time optimization. If I don't have this, if I don't have this template argument that this dummy thing here depends on, then all the key of functions I will generate for all the classes in my huge header file will be evaluated by the compiler. This return type will be calculated, and my compilation time of that single header file increases to 5 minutes. So this is nothing I wanted. So you need to have a template argument, and your return type has to depend on that template argument, and then the compiler doesn't look at it. And then it's fast, and well, you only evaluate the key of methods you actually use. Yeah, another question?
So basically that just means that if you did use, theoretically, each of these things, then you'd have to pay that.
Then I would have to pay 5 minutes. Yes, yes. That is, I haven't thought about it that way. Yes, yes.
But presumably most users don't use most properties in simulation.
Exactly. I mean, typically there would be types that are written to be used in such a constraint. So I could have done like a two-step compilation, find out which types are used with that key of constraint, only generated for those. But since this is just a valid expression in all of TypeScript to say, well, is that a key of that thing? I said, well, I can generate it for all of the types from the beginning.
This seems like something that would really benefit from modules. Because then you could compile it just in the module.
Yeah, good point. What modules would this benefit from modules? And I would only have to compile it once. Yeah, potentially. That's a good point for the standard libraries. Yes. OK, and then how does that function declaration look like? Well, I would, as a C++ programmer with Stockholm syndrome, I would say it looks pretty similar to that one. Could be worse. It could be worse. So I can actually say, thanks to Boost HANA, that this event listener callback should be a function that returns an any, and then it has some typey thing, which is, again, the result of calling keyoff and then looking up k in that map. So this part isn't so bad. I forgot why I need the plus, and then I need this type name decal type thing, because it's C++. Otherwise, I thought this was surprisingly good. Someone's laughing. It could be, considering my expectations, yes.
Is the plus trying to coerce out the raw function pointer from the lambda? I can't tell if there's a closure there, but if there wasn't, then why use this to function?
Sorry, what? Sorry, the plus. I really don't. So there's, I think the result of that, no, I remember what it was. The result of looking up K in that boost HANA map, if you go back, is I think HANA type C keyboard event. I think that's what it was. And I need this thing. And I need to get it out of the HANA type C thing.
So the iterate plus is the identity operator that extracts the thing. Nice. Oh, great. Okay.
Yes, that's
It's almost an identity, but we're going to change the type operator.
I mean,
That's-
that's what plus does in C++ and a lot of other contexts.
Does it change the type?
Yeah, lambdas convert to function pointers, short converts to int.
Oh my God, when did that happen?
It does
Wow.
integer promotions and converts it
Yeah.
to something that you can
Yeah.
plus. If you have like some type that is implicitly convertible,
I think that makes it worse for Dave. That this trick exists more often. Yeah.
Okay, go to the next slide. How complex is the function body of the add event listener is in C++?
Sorry, say it again.
How complicated the body of add event listener is in C++?
The body is just the call to JavaScript.
Is that possible to generate a whole bunch of overloads then?
I thought about this was one of the other things that you could have done traditionally. That where I said here, let's use an enumeration. You could have used maybe tags. Tag.
Well, I mean, the constant string literal can have their own type, so you can just overload it on the.
Yeah, but it doesn't have to because there are a lot of mouse events. Mouse enter, mouse leave, click, they all take a mouse event. So overloading on the mouse event isn't enough. You have to specify which event you want. But the overloading would have worked if I would have said instead of doing this magic string literal, I could have taken tags, for example. I could have generated tags and said, well, this is the click event tag type.
I know, but that's the same.
Yeah, but then I could have generated overloads, yes. But I thought there were several things. First, I didn't want to generate all these overloads. But already generating those tags would be annoying because I would have to generate the union of all existing keys to generate then tags for them all, so I don't generate the same tag twice.
Oh, I can talk to you later.
Yeah, okay. Okay, so this is the pretty solution. Okay, and then last but not least, my last code example, I said, well, of course we can not only do this with the built-in types, but we can do this with other JavaScript libraries. For example, with the JavaScript library from Tableau. And well, how do we do this? Well, here I have a little project, can show this off as well. In CMake, you can pull Typescripten from GitHub, include our little Typescripten CMake magic, and then down here say, well, please add a Typescripten target that will compile the DOM interface description and the interface description for Tableau and just put it into this header. And then in C++, I can create a little visualization. And what do I have to do? I think I just have to get the place where I want to insert it. Okay, I can't type anymore. It's so cold today. Okay, I think that's it. And then what kind of visualization it is. And then this is it. Okay. Okay, well, now this doesn't work like this, of course, because it's Tableau, and I have forgotten the Tableau namespace. Okay. Okay, now it worked. And now we get this little Tableau visualization of a musical that I've heard was pretty popular in the US. My kids liked it too. Okay, so that almost finishes my talk. Now we've seen how we can do type-safe calls to JavaScript from C++. Now, there are some caveats. So this project might be superseded. There's a... That wasn't me. I can keep talking. There was... there's a proposal called WebAssembly interface types, which should make it possible for WebAssembly to directly call methods on JavaScript objects. But that's still very early, and as with the ISO standardization, it's probably a good idea to experiment a bit with such features because before you, well, standardize them. And even then, they would probably need some C++ headers to like talk to JavaScript objects usefully.
Yeah, it probably ends up being a library API. So
Yes, I mean the WebAssembly part is all good and fine, but you need the C++ support for it as well. Yes, it would just eliminate this ugly bridging code I have in there.
So for the last image when you had that Tableau
Yeah.
set of widgets, I guess, for the Hamilton, was that I didn't see you importing in the C++ code anything other than the regular JavaScript DOM.h.
It wasn't the Java. It wasn't the CMake. That's why I showed the. That's why I showed the CMake. Shall we wait for the projector?
So you don't need an import in the C++ directly.
Exactly. No,
It's part of the build.
it's part of the build. It was all put into a single header essentially. My tool just.
Dash include in the build?
1 second.
He was generating a header.
I'm generating a header. Here's the CMake thing, and that says take those interface definitions and put them all into one header. I don't care. And yeah. And this is what it looks like with a lot of forward declarations and stuff. But here you see in the beginning some Tableau mangled enumerations, for example. Yes.
But if you wanted, if you go back to the CMake,
Yeah.
like you could have split that up and generated 2 headers.
Yes. Although it's probably not that easy because these things have dependencies. So this Tableau thing would probably require like in the TypeScript world, in the TypeScript parser world, this all exists in one, in the same space. So this probably depends on that anyway. So it would pull that in. So if I would do this twice just to generate a header just for this thing, I would have to do the work twice, I guess. So I don't think that's that easy. It's theoretically possible, I guess, but I don't think it actually makes that much sense. Because these things have dependencies that are pulled in and that are parsed twice. Okay, so I was here. Yeah, WebAssembly interface types. It's still a long way to go. I think Rust had them for a while, and they pulled them out again. So we are on the same page here. And then I thought, well, using that interface with the strings that I pass to JavaScript that have to be evaluated on the JavaScript side, that probably has some performance implication. So I tried to measure it and made a very small benchmark, very simple benchmark. I just make 1 million calls from WebAssembly to JavaScript. The JavaScript function does nothing, it just increments a number. And I wanted to measure what's the overhead of my approach. So how fast is it when I just call an extern-C function, when I do this macro embedding, and when I make this call with 2 C strings that have to be converted to JavaScript strings, and which probably also has an effect on the optimizer in the JavaScript runtime because I don't hard code those accesses. And that's real. This performance impact is pretty real, of course. Although Elon Zakai already essentially told me what I should do. So let's put it that way. What I should try to make this faster. Yes, that's converting the C strings probably. Okay, and what are the remaining challenges? Well, first one, emscripten integration. And then the next step would be, or at the same time maybe, to test this tool against a bigger input, for example, against this repository of 7,000 types to see where it fails, what I have to do next, and see what are the most important language features to make this work. Is it generic constraints, or is it literal types like these? And then probably in the end, performance, if that's actually necessary. OK, yes, GitHub link again. And thank you for listening. Thank you for coming to my talk. More questions? Yes.
I may not familiar with the JavaScript's internal string encoding. I saw you used the narrow encoding on the C++ side.
Yes. That's the only thing emscripten supports, I think, narrow strings. I think there is.
But there's no, like, if I remember correctly, JavaScript engines itself use Unicode 16.
Yes, that is true. And there was some reason why I forgot about it. That's something I don't know about the emscripten internals. But even in that simple function that only takes a car C string, I think on the JavaScript side they have to make some character conversions. It's not actually the same encoding, I think. Yes, Dave.
Oh, yeah. Actually, I wouldn't be entirely surprised if JavaScript implementations are actually using UTF-8 under the covers, even though they're required to expose UTF-16 as an access method. We went through a big process of converting Swift to doing that effectively, and it is technically possible, and it was a huge win for Swift, for what it's worth. In any case, what I really wanted to say was that the performance benchmark I wanted to see is the one where you had JavaScript code doing the main, calling that trivial function, versus your C++ code doing the main.
But is it so Dave said he wants to see another performance measurement of, but what exactly is it you want to see? Do you want to see like the pure WebAssembly side? How fast is it to, I don't know, accumulate 1 million numbers in a std vector?
I want to take that out of the equation, right? See, like I know you're going across the boundary.
Yeah.
And I know you have a JavaScript thing you need to call, or a WebAssembly thing you need to call, right? But what I want to find out is, what is it costing you to bridge to that from C++?
This is yes. I had more performance measurement that measured this as well. So how fast is actually the JavaScript side if I do it only in JavaScript versus if I do it only in C++? And so
that's not the measurement I wanted to.
Yeah, that's also not the measurement.
Yeah, I do it only in JavaScript versus do it in C++ calling JavaScript. That's what I want to find out.
But how is that different from that? I mean, it's measuring.
Well,
this is doing it in C++ and call. It's okay. I don't have the pure JavaScript version here. That's true.
Yeah.
Yes.
So that extern C function only has to do the work of, I don't even know what you put in there. Did you increment a number?
Yeah, I incremented a number.
Okay,
yes.
but that's a C++ number increment. So I know what that cost is. I'm interested in the cost to get across the boundary.
Yes.
Right? And I don't feel that that's what this is telling me.
No, this is just telling you how the overhead of my approach of doing that is.
Well,
there should be something.
It's telling me the combined overhead of your approach to getting across the boundary plus the operation that it's doing in JavaScript.
Well, that difference, those 382, they are my overhead. Because this is doing the same work, but with a different way of calling it.
Okay, maybe I'm just confused. I don't understand yet.
Yeah, so these are, there should be another one on the left side. How fast is it to do that actually in JavaScript alone versus maybe in WebAssembly alone? So you have a better measurement of, this is the overhead of an extern C call, and this is the overhead of some asm.js macro thingy, and this is my overhead. So there's something missing on the left side. The two pure approaches, maybe. Yeah. Yes.
So at the very beginning, you showed us a command line where you had to pass in some extra things.
Yes.
It's very experimental.
Yes. It's in my fork. Yeah.
Yes, and then you showed us some CMake. So is the CMake function adding in those flags, or like what exactly were those flags doing again?
So the flags are so there are two things. So the tool exists in GitHub, and as a first step, I thought, okay, so people can use that. Should at least make this CMake integration that I've shown you in the last example, where I give you a CMake function, and that just calls the pure Typescripten binary, passes the Typescripten compiler arguments, and does everything manually, so to speak. But now when I want to integrate this into emscripten, I thought again about how do you usually specify command line arguments to a compiler. And I thought, well, it would be elegant. I thought this was the most elegant way of doing it, of saying I have the CPP file that depends on a JavaScript library. So please generate this header for the JavaScript library for me, and put this succinctly in a single invocation in a readable way. So, and then internally it does the same thing as the CMake integration, of course. It parses the command line arguments and notices, I have to call this Typescripten compiler first, and then it does this for you. Yeah. Yes, Sean.
I'm wondering if there's an appetite within the emscripten dev community to maybe augment the C++ front end to support the additional types that JavaScript has that C++ doesn't, and force you, just forcing you to do all these workarounds. Like, could you expect something specifically for emscripten to do the JavaScript union types? That's what Dave said earlier. You could extend the language. It's hard to do at the standard level, but if it's specifically this kind of project, it seems like the scope is more focused.
In other words, if you were Sean and knew how to write a compiler,
If I had a better compiler, yeah.
Really fast because you're Sean. would you take
Yes.
that on? Would
Yeah.
you do that instead of making a library to do this bridging?
Maybe, yeah.
Well, it's out of the scope of this project, though. It's more of the emscripten compiler, right?
So, yeah.
But like, I think the emscripten compiler doesn't have its own C++ front end. It's just a backend.
No,
right?
it's just wrapping Clang, of course. And then it has a lot of other tools to strip and whatever and link. But yeah, it's just wrapping Clang. So
Well, this whole problem of language interop comes up over and over again, of course, right, with the N different languages.
yeah,
And so there is a good argument for some kind of facility built into compilers for doing that, right? So that we don't have to repeat that work.
mm-hmm.
But nobody's designed that as far as I know.
No, and I mean the other ones. Well, usually we fall back to this, right? We do like extern C, and languages can do that sometimes, and then sometimes this.
But I mean, when you have extern C and you want to make it a little nicer, because you always want to make it a little nicer,
Yeah.
because that's really horrible.
Yeah.
You write a fancy C++ DSL to wrap the extern C API.
Yeah.
Because, who's Python? I've been here.
Yes.
I want to understand Dave's comment a little more. Are you saying that there can be a compiler that parses TypeScript definitions and produce C++ AST?
Well, sure there could be.
Okay, then what's your original comment is?
Sorry?
What's your original comment is?
My original comment was, I was trying to say, so for the case that you're talking about, that functionality belongs in a TypeScript compiler, right? Because it has to process the TypeScript. But in any case, for any language that wants to vend itself to other languages, there's a common set of work that happens to vend the same API to different languages, and there's no common language for expressing that bit of work, right? We don't, you might use PyBind 11 to expose your C++ to Python, and then you'd use this to expose your C++ to emscripten, and then there's another one for Ruby and another one, right? And so there's something to be thought about how do you unify that and what language support would help.
But I'm sort of not sure which direction you are going, because if you mentioned pipeline 11, that goes from C++ to Python.
Yes.
But for that direction, like there's a swag.
There's swig.
Yeah, that's that widget.
Yeah, I know.
That's
I know it does that. It's not a great solution.
I don't want to use it either. But
Yeah. So I mean, that's not a great answer, and you have to write a kind of completely separate interface definition that needs to stay in sync with your C++. And anyway, so for every language that interoperates with other languages, for TypeScript also, for C++, it would be great to only have to do, if there's any extra work you need to do to interop with other languages, it would be great to do that work once and have a common set of facilities for doing that. Somebody who's thinking about these things, you know, maybe that's a project to take on.
No, interesting. No. Anything else? No, then. Well, yeah. Sorry. Keep asking.
Can you go
Sorry.
back to the CMake example?
Yep.
Is this generating one header once it's
Yes.
Is it using the precompiled header? Or can it?
It can. Sure, it can. I did that in other projects. Yeah,
Okay.
it could.
I suggest you to give it a try. You may help.
Sure. Yes. Sure. Yes, I mean, in the emscripten logic, I think there's one way where you can specify. So I thought about how do build tools do this, and of course, if you have a more complicated project with several CPP files, you don't want to compile the entire library for every CPP file. So of course, there's an invocation without a CPP file where it would just generate the header, and then you can do this once and then generate the precompiled headers and then include those. Yeah, sure. Okay. Well then, thank you very much for coming, for listening.